So thank you, everyone, panelists and attendees, everyone all together. Thank you for joining this really educational and just interesting event on copper and additive manufacturing. We're going to get started with a tiny bit of background. Some of you may know Deep Tech Showcase. I'm Yuval Herman, Director of Events and Network Relations at Deep Tech Showcase. We're going to have amazing key speakers from Elementum 3D, NASA 3D Systems today. And I'm going to do my best to speak as little as possible so that you guys can hear as much as possible from the people who you are here to hear from today. Just a little bit of background for everyone who's joining about our network at Deep Tech Showcase. We run and facilitate a very active ecosystem with the goal of helping bringing more deep tech into market. We work in every single industry besides life sciences. That's kind of the only area that we're not into. We are supported by our partners Eagle Point Funding, who are grant specialists, who some of you also may have heard of. And our job in that kind of paradigm is less on the grant side, but more on the networking side and bringing the different heads together in many different industries. So today we're focusing on 3D printing technologies, copper and additive manufacturing, and all these buzzwords and great industries that are related to the event today. So what we're trying to do is help founders kind of cross that innovation valley of death by finding the right partners, as well as help the stakeholders on the government side, the industry side, the corporate side, and even the investment side also find those key partnerships that are going to help support companies developing truly innovative and novel technologies like we're going to see today as well. So like I said, our ecosystem is built out of three parts. We have startups at the beginning of their way, trying to develop their technologies and looking for new synergies and partnerships, investments, and et cetera, et cetera. On the right here, we have tech investors who oftentimes have an issue finding the truly innovative products in markets such as deep technologies that are very vast and very wide. And then last but not least, and really relevant to today's event, the industry experts, whether it be the great speakers we have today or other people within our network who can come and add their input as thought leaders in their various industries and help kind of support this network that, as I said, pushes new technologies to market. We run various different events. An event that's a little different than today that we're hosting soon is our Autonomous Systems Showcase. We have a event for companies to pitch to different stakeholders within our network every month. People who are interested in autonomous systems, even though it's not the industry we're going to focus on today, are welcome to reach out to me at Yuval Deep Tech Showcase. Happy to send an invite. Look it up on LinkedIn, our website. It's up there. And an event that's coming up that's more similar to today is an Ask Me Anything with Matt McGregor, mission engineer and acquisition subject matter expert at U.S. Air Force and Mitri Corp. And that's going to come up on the 15th of November, where anyone with a curiosity and wants to learn more about working with the Air Force and things of that matter are welcome to join and ask your question. Moving on to today's agenda, most importantly, we're going to start off, or we already kind of started off with an opening presentation by yours truly. Secondly, we're moving on to, in just a bit, to our first presentation by Jacob Mechterlane, which is going to be past, present, and future of copper and additive manufacturing, representing Elementum 3D. Then we're going to go to exciting developments in coppers and alloys by Scott Green, representing 3D Systems. And last but not least, we're going to have a presentation on NASA's advances in additive manufacturing of GR-COP alloy liquid rocket propulsion systems, represented by Thomas Teasley of NASA. And then we're going to open up with the time that's remaining with Q&A with the audience, and I'll go in a bit of how that's going to work. If everyone looks at the bottom of your screen or at the top of your screen at the toggle bar, you'll see a Q&A button. Audience members are welcome to write their questions when they come up, when it's hot. as people are presenting. Each presentation is going to be around 20 minutes, but we're not going to hold the speakers to it too heavily. We're not going to be too strict on that. But there's going to be around 20 minutes. At the end, we'll try and answer a few key questions. Every speaker will be able to look in the Q&A, pick out a few, and answer them live. And then we'll move on to the next speaker. And at the end of the event, we'll go back and we'll go over questions that haven't been answered yet, as well as open up the floor to more questions. But it will all be through the Q&A. So if you have a question, don't put it in the chat because that can get a little lost. Make sure to put it there in the Q&A, and we'll make sure to kind of facilitate it. And that's pretty much it. I'm gonna move on, and without further ado, I'd like to invite Jacob Nectarlane of Elementum 3D.
All right, thank you. Let me see if I can figure out how to share the presentation here.
Yep.
Is everyone seeing that?
Perfect.
Great. Yeah, so I want to start with a little bit about who is Elementum 3D, if you don't already know. I started Elementum 3D at the end of 2014, really with the goal of increasing the additive manufacturing materials library. And because I don't know anything about polymers, I focused on metals, and really got to dive into that, as you know, my background from the Colorado School of Mines in metal matrix composites and castings, really took that knowledge and then, you know, married some of the things that I was doing in my PhD studies with 3D printing, which I had never done before. Since then, we've released quite a few new materials, materials that people told us were not possible, everything from high strength aluminums to copper alloys, which we'll get to dive into today. We're located in Erie, Colorado, just north of Denver. We're actually going to be consolidating and moving to a new facility soon, so that's exciting as well. But yeah, just to set the stage, we have printers in-house, but our real business is supplying new materials and new settings and print settings to be able to print materials better. Just so we're setting up the context here. There's a number of different alloys that we've been printing, so we're not just printing copper alloys, but I really want to focus in on what makes copper difficult, why, and what is out there that makes copper different from some of the other materials. But certainly there are challenges in other materials that I think are completely different. So the solidification structure differences that are in like aluminum alloys or nickel super alloys don't really occur in the copper alloys. And that would initially make you think, well, copper then is a good choice. But really it comes down to materials that are hard to weld typically are hard to print. And so finding materials and making materials more weldable is a pretty important part of making them printable. So really moving to the copper alloys in particular, we started printing copper alloys in late 2015. And you know, there's a lot of, I think, some difficulties that come with that. There were a lot of questions. There were a lot of people that said it's not possible. But to start, there just wasn't any material available. The powder wasn't available. So finding the correct powder and being able to supply powder that would flow in the systems and spread in the systems properly was the first difficult task. And including some of these alloys like the copper, aluminum, bronze, we started with essentially mixing multiple different materials of master alloy to be able to make that material when we were doing our first study on it. And then from there, you know, it was the challenges of, well, the conventional wisdom in the industry was, well, you can't print copper unless you have something like a green laser or something, you know, extra because of the reflectivity issues. So copper in general does not want to absorb laser power and laser energy. So one of the advantages we found, though, was aluminum doesn't really either. Now, the advantage of aluminum is its lower melting temperature, but there's still that same problem of they both would like to reflect these particular wavelengths of energy. And therefore, the conventional wisdom was you had to go to green lasers to get this to work. That's really where I think we kind of came in and said, well, hold on, that's not exactly true. Because it's a powder, when the laser interacts with the material, it actually, even if it reflects, it has multiple chances to absorb because it can reflect off the individual particles of the copper, which then allows us to do things like melt the material, but you have to move the laser very, very slowly. So then it was uneconomical. So we ran into some issues right away with it being uneconomical to print, it leaving high porosity, and being able to get to like 94, 95% dense with a print. And that just wasn't far enough. So that's when we really started diving into, as it says here, we found a process in which we could produce the copper material with a coating on the powder itself. So we could actually start printing pure copper material with that coating that enhanced the absorptivity. So all of a sudden we could get to very high densities. We could get to full hermicitivity, so that when you're doing something like a cooling channel for a complex chip such as this, or you're doing a heat exchanger or something along those lines, it doesn't leak, and the productivity was much higher. So that was really some of the things that really started opening up that door, where we started finding applications. And one of the first applications that we really started to identify was heat exchangers for servers. So servers are currently limited today by the amount of heat they produce. That's most of the energy that's spent on running server farms is spent on electricity, which goes into cooling and powering these systems. So one of the big ways to help reduce the power was to improve the ability to cool with less power. From there, we're now getting into the point where the new processing chips are so powerful and have such a high energy density that they're no longer able to cool those chips with the current technology. The next generation of chips are going to have to be limited because of the way that they're cooled. So we're really getting into now applications that are specific to additive, in which additive can make shapes and designs that just aren't possible or aren't economical even with traditional manufacturing techniques. Then we started getting into some conversations, and I think other presenters today will get further into this, but we really started printing with GR-COP42, which is a NASA-developed alloy, and started to look at that for high temperature applications. We started working on that primarily with how do we process it? What are the printer settings? How do you go about making this material and printing with it? Because of our experience in the copper 100 and in other copper alloys that we had begun working on. But again, a lot of this work had been being done and has been being done for a long time now. As it says here, starting to print in 2014. So we started looking at, well, what are some of the things that are going to really limit the usefulness of being able to print these things? And there's some components within these rocket engines that I think we identified as places where you don't want to have to take two parts and bolt them together or weld them together. You'd like to be able to print it all as one piece. And so one of those is a product that we began developing with Mass and Space Systems called Permi-AM. Again, this is essentially a process in which we can print it all as one piece, but have different functionality within the part. And so we can have a single component all printed at the same time, but have a certain area that is intentionally porous in a particular way that helps us, regulate flow of gases and fluids. And we've really gotten to dive into that more recently on more recent projects as well. Then there's other materials. So aluminum, copper, bronze is almost 50% copper, 50% aluminum. But the real advantage here is, well, we first started looking at it actually because of its color. It's used often in things like, fake jewelry, that sort of thing. And so the color was actually something that we were first approached on by customers, where they were looking for something that had that kind of gold color to it. But ultimately, the real applications for it end up being in high corrosion places. And so we've started to find a number of naval applications where we really got to dive into this. But like I said, again, one of the biggest challenges with this material was really being able to source that particular alloy, because all of these different things you have to do, you have to source the material from somewhere. And if it's the first time it's ever printed, finding someone who's going to do a custom run of a particular alloy is not something that's easy to do. As it grows and once it gets into production, that certainly becomes simpler and more straightforward. But I think that takes a while before, you know, a particular material is in full production and therefore is readily available and less expensive. So now I'll move on a little bit more to the present. What's going on today? Where are we really going after different applications? We found a number of different, I think, exciting applications in the semiconductor world, from cooling to heat exchangers in data centers. But I think some of the things that I didn't realize were really going to be, I think, applications that are really starting to take off with our copper and copper's around now that copper is a more commonly printed material. We're starting to see RF antennas. We're starting to see things like image here in the middle. That's a induction coil. Making induction coils with even thickness of walls is actually very difficult to do. To be able to bend a tube like that without having thinning of the tube in one area and thickening in the other area as you bend it is not easy to do. And particularly as you're going after something that has really specific dimensions to it, like an induction coil, additive can all of a sudden become a really interesting choice for having a specific design on something along those lines. And then certainly rocket propulsion. So we're working with different groups like the University of Texas. They've been putting together, you know, and there's been competitions within student groups for looking at the next generation of rocket engines. Certainly, we've done some work with NASA and with other commercial partners as well in printing GR-COP 42 and other high temperature coppers, which we'll get into in a second here. But I think there's a lot going on now where I think a majority of rocket engines will be printed in the future. And I think finding that sort of application within additive has really been the key to the growth of additive over even the last 2 years. Finding applications where it just makes more sense to print it than it does to make it through conventional methods. And I think that's really exciting to see, even you know, accessibility to technology like this, even down to the university level, where they can do things that just weren't possible even a couple of years ago. So yeah, within GR-COP, there's a lot of optimization, and I think this goes for all the alloys that we work on. Is, you know, you can print just some simple cubes and say, well, done, we've done it, it's good to go. That's very different than being able to make complex geometries and to make geometries and shapes and overhangs and thin walls, and being able to do that in multiple different systems. You know, you hear about, well, I've printed it in, say, a smaller system like an M290. You should just be able to then copy paste and put that into a larger system like an M400, even from the same manufacturer. And it's typically not that simple. There's a lot of things that are different within that process, from the gas flow, from the way the material deposits, but even things that don't seem that straightforward, like the filters. The filters within these systems, we were finding that in long, tall builds, the filters were clogging really quickly, which all of a sudden meant that our gas flow wasn't then consistent throughout an entire height build. So all of a sudden we were looking then at things that we hadn't initially considered and that aren't challenges in other materials, that are challenges specific to some of these copper alloys, which is that things like the clogging factor, things like as you're at temperature, you have to wait for the entire chamber to cool down or else you oxidize the powder. There's real challenges there that don't exist in just about any other material that exists in these copper alloys, not just GR-COP 42, but coppers in general. And I think there's some exciting steps and advances forward, not just in the processing and in the procedures, but then also in the equipment and the printers that are now coming out and have different advantages. So I think there's big strides being done to help address these particular concerns and issues. So yeah, it has a couple of passes here of the laser. You can see you do not need a green laser. This is a standard off-the-shelf system. It can print copper, it can print GR-COP 42. And I think that's an important aspect of, there may be advantages to like a green laser or something along those lines, But there's also disadvantages, and those green lasers are typically harder to focus down to a very small spot size. And so you get these kind of pluses and minuses within these different materials that I think are important to really dive into. I already talked a little bit about Permi-AM and that technology and the different designs, but we've gotten to dive into copper, nickel alloys, all sorts of things for these, you know, what can be pretty complex geometries. But I'm actually excited for the future of Permi-AM and where it can go, because it's not just in propulsion, but we're starting to see other industry applications in oil and gas, even combustion engines, where there can be big advantages to, you know, something that can control or moderate the flow of gases or fluids. So there's a couple of things where we can see cost savings of, you know, not having to be able to attach two pieces together. We can get turnaround times on prints much faster, and we can do things like swirl the fluid or have the fluid, you know, exit at certain speeds or have different pressures applied. So there's some really, I think, interesting application space that we're investigating today that hopefully will be applying to, I think, really, really interesting applications in the next 3 to 5 years. What we're doing with GRCOP 42 today, you know, I don't want to go too far into it because I think there's going to be other people that really get into this, but I want to talk about some of the issues with GRCOP 42, which tends to be in the atomization and supply chain and the cost of that material. It's very difficult to make GRCOP 42. It contains these kind of chromium niobium compounds, which have a much higher melting temperature than the copper itself. So you have to go to a very high superheat in the copper. So that's what that means is you have to go to a temperature well above the melting temperature of copper to melt those precipitates to get a good distribution of those elements so that when you do atomize, you have a nice consistent powder. Well, the problem with that is then you start to dissolve the crucible. And so as you're at these very high superheat temperatures to dissolve those chromium compounds, you end up with having that kind of race. Do you dissolve your crucible faster and therefore have contamination from the crucible, or even bigger problems than that, before you're able to atomize all of the material, which then limits you to kind of the size that you can do at one time. And so I think there's a lot of challenges with that. And there's a lot of great companies doing some atomization of these materials and really getting and dialing in and getting better at this and finding new crucible materials and different ways of doing it. But it is still limited, and the industry in general and the volume of powder that's possible to produce is really limited by some technical concerns, not just the commercial concerns of making GRCOP 42. And so there's then the supply chain and cost problems that go with that, and that 2 years ago, we bought the majority of the volume that was available to the rest of the industry. As a small company like Elementum, that's a problem. And so we identified that as an issue of GRCOP 42 performs quite well. There's great performance out of that material, but if you can't find it for a lot of other application spaces because it's too expensive and it's hard to come by, and therefore you have to accept kind of lower quality product in some cases, or product that's outside of a very defined specification because that's all there's available, that causes issues. So what's the solution? This is really what I want to talk about the future. We've been working on, and I know there's a lot of different people who are looking at solutions to this, either atomizing GRCOP faster and better and in larger quantities, but also then looking at maybe alloys that are similar to GRCOP 42. So that's really something that we're working on. It's not released yet, and we're still working on it. But at the moment, we have some really interesting results with what we're calling our hot copper, which is a high temperature copper meant to really, perform as well or better than GRCOP 42 in conductivity and high temperature mechanical performance, but have it be way easier to produce in large quantities and therefore easier to source and therefore available for other applications other than just rocket engines, which I think then makes it really interesting to expand that process. And the way that we're doing this is through our particular technology called reactive additive manufacturing, which I won't go into today or really discuss today. There's a lot of other things that we've talked about other times, but if you want to know more about what we're doing with this and where we're going with our hot copper, happy to dive into that further in the science of what makes this different. The future of Permi, there's a number of different alloys that we've been applying it to, not just the GRCOP 42, but I think there's also different things where we're going to be start looking at the flow patterns and start looking at how the fluid or the gas is flowing through these pores, and therefore how does it come out on the other end, and then controlling that to do things that just weren't possible without 3D printing. So not only taking advantage of the pressure drop, but taking advantage of some of the other advantages to this kind of intentional porosity that we're printing in. And then we recently were awarded an SBIR to go after copper nickel alloys. And so we've been looking at this over the past about a year. We've been looking at this with really looking at copper nickel alloys for RF components and for other components within the naval space, which I think there's some interesting reasons on going after some of these copper alloys that just weren't really achievable in the past. And because of radio frequency RF applications are really complex shapes, all of a sudden we found that there's real business cases for additive that just don't exist because of the complexity, because you can do things that just aren't possible. So if you see this part on the right, I think that's a really good example of a complex part that then becomes more achievable with 3D printing than it is with, say, trying to braze every one of those connections together at really tight tolerances. So like I say, there's a number of things that we're working on in the copper space. There's a number of other alloys that we're looking at, maybe in the future of development of looking at very high thermal conductivity coppers. So going to copper alloys that have higher thermal conductivity than the wrought material. And then looking at how does that affect then the landscape and the applicability of additive for a number of applications that were just kind of locked out in the past. So at Elementum, that's really what we focus on, is developing new materials, developing new alloys, and copper has been one of the things that we've been leaders in for a long time now. So that's us. That's what we do. Happy to maybe have a look at the Q&A and dive in.
Thank you so much. Thank you so much, Jacob. That was fascinating. Like I said, we can open up the or you can open up the Q&A, choose a couple questions that we want to tackle now, and I'll just say again, anyone who joined maybe didn't hear at the beginning, if you have a question to Jacob or to any other of the speakers going forward, just write it in the Q&A and add at the beginning to Jacob or to Thomas, so that when we come back to it at the end, when we have more time, we'll be able to know who to address the questions to. All yours, Jacob.
Yeah, so the first question here that I want to talk about is the burn off of a coating. So the coating isn't a polymer based coating; it's an oxide based coating. So I don't think that there's any difficulties there of having problems with the burn off. Essentially, you might get some vaporization of it, but then it's pulled away by the vapor pull. So when we're measuring thermal conductivity or looking at it under SEM, yeah, there's no like residual coating. That coating is super thin. Let's see here. Scan strategies. So scan strategies, I think, is a really important piece of this. We've done a lot of different things looking at scan strategies on copper, including double scanning. The problem with double scanning is then you start to lose the advantage of the powder in it being rough. So you don't then get the reflections and the extra reflections. So that we found that once you melt the material, that material then is very reflective, and therefore it's a lot more difficult to put more energy in. So we've done things like control the oxide and therefore get higher thermal conductivities from doing double pass, but it slows your build speed down quite a bit. So I think there's there's pluses and minuses there. If you have an application that needs much higher thermal conductivity, doing a double pass can help. But if you need good thermal conductivity and build speed, then it's, kind of balance there. Yeah, the coating does not alter the chemical composition. Like I say, it's still commercially pure copper at a very high purity copper, but it's not ultra high purity copper anymore.
Awesome. We're good on
Yeah.
time if you want to do another one, Jacob, before we continue to stop.
Oxidation behavior of GR cop powders. We found, and we've tracked this, this was one of the things that we specifically were looking at, was the oxidation behavior on GR cop. GR cop tends to not oxidize readily, and many coppers do not oxidize readily below about 50 degrees Celsius. So the real trick here is to keep the material below a certain temperature, which is one of the reasons that you have to leave the material in the printer for a long time to let it cool down on its own, which can then affect the return on investment there, because you have an expensive piece of equipment with material that's just cooling. But yeah, it's important as we're monitoring the oxygen level in the material and in the powders. You can expose it to air. It's not like you have to, have it in argon at all times or something along those lines. It's just keeping it under an inert atmosphere while you're printing or while you're at temperature, I think, is a really important aspect of GR cop and coppers in general. But specifically GR cop, we've seen it oxidize very quickly if you're still at elevated temperature when you're working with it in air. The percent ISCS, so we see, and we have this listed on our website. Like I say, you can get to higher conductivities if you do double passes, but we see about 80 to 85% ISCS when done properly with thin walls and other scenarios and overhangs. Depends on the shape of the part and how you're measuring that conductivity. We found that can be wildly variable, but we've seen everything as low as even 70%, depending on the application. So we list on our data sheet 70% ISCS to kind of cover that. But certainly, if you want to get more into a specific scenario or a particular part, we're happy to talk about what that would look like for that part, and then how we're measuring that thermal conductivity. That's, I think, a controversial topic, is how to measure conductivity properly in these different materials. And a lot of people are doing it the easier way, which is to use electrical conductivity and then kind of try and marry that to what your thermal conductivity is. And that works okay. Yes, copper matrix composites that's how we're addressing the hot copper topic. So yes, we are looking at copper matrix composites.
Awesome.
Oh, we have time.
So yeah, so we'll continue. The questions are awesome. Keep asking. Like I said, we're going to move on to the next speaker. Thank you so much, Jacob, for getting us started. And we're going to move on to Scott Green from 3D Systems. And there's going to be a whole portion to go back to any questions that weren't answered at the end of the 3 presentations. So hold tight. We're going to have 2 more great presentations ahead of us, and then we'll continue with the Q&A as well.
All right.
Awesome. Scott, are you able to share your screen?
Yeah, can you hear me okay?
I hear you great. We just don't see your screen yet. Now,
there you go. How about now?
Awesome. Just put it in full screen. You got it. Awesome.
All right, guys. Hey, so yeah, awesome presentation, Jacob. This is a great collection of speakers because we're all going to probably take a slightly different angle on the subject. And my angle on the subject is definitely going to be trying to at least raise awareness in the vast amount of applications and at least what we're doing in 3D systems. So we have numerous different copper alloys, and I wanted to kind of show you a sizzle reel of really great applications we have that we've been working on. Yeah, so let's go ahead and kick it off. I'm Scott Green from 3D Systems. I'm principal solution leader here. And if you're not aware of 3D Systems, we're a global company. Most of our metal printing and most of the R&D in metal is happening between Littleton, Colorado, Riom, France, and Leuven, Belgium. But we have offices all over the place that are focused on R&D of some sort, both plastics and metals. This is kind of how we're organized, just so you know. what's going on here. We're basically broken in half. On one side is healthcare, and on the other side is industrial solutions, half by revenue, and I manage a bunch of different segments, including semiconductor, part of energy, and academic and research. Generally, how we work is we take kind of holistic approach to working with our customer and bring solutions together with innovation and expertise. I think there's actually a really good way to capture this, which is what we call our tech transfer process. For any application we usually go through this like 5 or 6 stage process where we take a look at your challenge, we try to figure out the right solution for it. And we go through an innovation process, a development process where we help do design for additive manufacturing. We do just industrial design and design for manufacturing in general, which can include lightweighting, advanced cooling design. We've got a huge amount of expertise in cooling design, thermal design. And then once we go through that innovation process, we're going to go through the process of figuring out how are you actually going to make this thing. And we find the right machine material, build styles, any downstream post processors through our network, anybody who needs to do surface treatment or machining. We start to build this package of knowledge on how to make something. And that is very valuable because we're de-risking the entire process of using additive. And that's pretty key to scaling additive in industry. Is it's still kind of new for a lot of people. It is scaling really quickly in industry in general, but a lot of companies are kind of dipping their toe in, but there's still risk. Nobody really wants to buy $1 million risky machine or $500,000 risky machine. So we want to try to solve the problems up front so that it makes it super easy to invest and be successful at the same time. So then we go through this process again of some testing and production and scale. Just a little bit about us again. We work in highly regulated environments. It's half of our revenue comes from healthcare, medical device production, and healthcare in general. So we've got now almost 200 machines running nonstop, 24/7, 365 internationally. And we specialize, I like to say, in torque as opposed to speed. We run a little bit of everything that we have, and we try to be experienced in all the different processes of post-processing and finishing and all of our different materials so that we can be most agile to help customer needs. All right, so let's talk about copper, what we're here to talk about today. Now, generally, I just took a sampling of the past few years. There's always been some requests as a machine maker, 3D Systems, and a machine designer and vendor, and a user of our own machines. We're always getting the biggest breadth of requests from people. Okay, do you use niobium? Do you print unobtainium? Right, all these different things. And we've always gotten some requests for copper, but I will say that it's definitely rapidly increased in the last few years. It's kind of quiet for a while, a couple requests every quarter here and there, but it's actually rapidly increased. So there's definitely an acceleration in not only the implementation of additive in industry, but also copper applications in industry, and that's enabled by folks like Jacob and 3D Systems and other material manufacturers or vendors that are configuring copper to make it more easy in the process and finding novel alloys which are only bringing the most valuable parts of the element together with other very valuable properties to bring a valuable part to market. So here you can see some just basic industry ranges. Okay, we've seen it all across the board. Space access, space payload, marine defense, semicon, of course. Typically in the very infrequently, you're going to find copper in semiconductor capital equipment, but more frequently, you're going to find it in general like thermal applications not related to semicon process. Definitely general aero, auto, and consumer electronics. So what do? You've got all of these different use cases looking for some copper applications, and all by the way at different economic scales, right? So the marine industry is probably looking for okay, I need 100 parts and I have a budget that's, that's relatively good. Now the automotive or consumer electronics industry is like, okay, I need 500,000 and I need them relatively cheap. So how do you cover the breadth of all of these? Well, you got to focus. Now, this is what our metals portfolio was before we started to really focus on copper. So, we use 6061 from Jacob and Elementum 3D. It's great. But then again, we also have all these other materials available. So what we did is, in 3D system style, we laser focused on the concept and just crushed it. We went across the board and figured out, okay, out of all possible alloys that are being requested, which ones are critical, and in each one of these have different values and different reasons for being developed, and most are at very high TRL levels at this point. So here you can see we've got, I believe we're at 99.8% pure copper, copper nickel 30. This was developed with United States government for marine applications through Newport News Shipyard. It's something we announced about a year and a half ago and finally released to IMTS. So we're printing and firing on copper nickel 30 today. Copper chromium 2.4, copper chromium zirconium, both very similar alloys, which share parameters, and GR Cop 42. Okay, so you might be wondering which alloy is right for you, or which kind of configuration is right for you. And I'm going to leave this up a little bit so that you can kind of cross compare on your own. Now, on the far right hand column, we've got the kind of standard additive manufacturing materials. Okay, everybody's got ALS I10MG and titanium grade 23 or 5. So if you want to take a look at the comparisons between these different alloys and these materials, then they're up here for you to look at. Now, pure copper obviously is going to have excellent thermal conductivity and electroconductivity. It's not going to be as hard or as stiff as other materials. It's going to be quite soft. But there are definitely different alloys which give you advantages if you go left to right over pure copper as you add elements. Copper nickel 30 being quite interesting to us because it is a nickel copper alloy, which is giving us kind of the best, a good combination of copper properties, but also the nickel corrosion is really typically going to be the primary need for saltwater resistance. All right, now these alloys are printable on our mid-frame system, not yet available on our large frame system, TMP Flex 350 and Factory 350. Pure copper is in fact using a different optical configuration, and there's a good reason for that. As Jacob mentioned, there are ways to print it without a different optical configuration, with a standard optical configuration, and we did prove that too. But in order to really get the productivity and speed for production applications that our customers are demanding, we did go with different optical config, and that actually benefits us in an end result. Yeah, so if you're not familiar, DMP 350 and Factory 350 today are at 275 by 275 by 420 in height. And we pull a vacuum and then backfill with argon. So operating in almost a zero oxygen environment is great for oxidization and protecting and maintaining the quality of the material. It also allows us to achieve extremely good IACS results through our optical strategy as well as our chamber. All of this is driven by our 3D Expert software, which is an all-in-one solution for additive manufacturing. It allows us to design supports in any way you'd like, but we offer styles for the materials that we support. So it's pretty simple and easy. Also, you can engineer your own type of porosity on the surface or interior with the functional representation and implicit modeling. So it's a truly hybrid modeling software, which allows you to bring any geometry together into a single package for printing. So any part could actually include lattice, mesh, implicit, and BREP CAD, and supports all at once. Let's look at some application examples. Yeah, so commercially pure copper, we're absolutely seeing things like cooling tubes, and in this case, we printed on the Flex 200 fine spot configuration, 50 micron layer thickness. Yeah, and this is commercially pure copper. This was shown at INTS, and we'll be showing again at Formnext. And it's a little cross section through a cooling tube with a heat sink inside. And one other thing is we do offer a smaller volume. I'd say that our Flex 350 is, and our Factory 350 is our like bread and butter mid-frame system. We also offer the DMP Flex 200, which is a slightly smaller system with a finer spot size, really fine spot size. So we're able to not only cover the kind of high-speed production copper applications where kind of general layer thicknesses satisfy the need, but also we worked very hard to do super thin wall thickness, 150 micron and lower wall thickness. But that's only available on our Flex 200 because the special optical configuration, right? It's got a smaller spot size. We use a compressive roller, and we can do thinner layers and with thinner powder and smaller powder. So we're really able to cover the different kind of applications and needs, fine features, high precision, and in one range, a mass amount of different materials available in our mid-frame workhorse. Again, yeah, commercially pure copper. These are it's a commercially pure copper heat exchanger. This would be at Formnext as well. Exceptional resolution and density here. Really blown away by the density of copper. And what I will indicate is that we have, on average, 100% IICS without heat treating. That's one issue that you're going to see in the market is many other companies in the industry are going to say, yeah, you can get up to 100% IICS with heat treating, because one of the tricks that you'll see is, yeah, you can print copper, but hey, it's porous as heck. So you have to go through a heat treat to kind of shrink it down and basically melt it together and solidify it. And that could be okay for your application. That's not the way we work with 3D systems. You get parts that are almost completely dense coming out of the printer with 100% IICS up to 103% IICS we've seen. So that no heat treat is required. With heat treat, you just gain marginal advantage on IICS and density. So it's not, heat treat on commercially pure copper is not a requirement to get your full density. Okay, it's not like a binder over powder part where you have to get through a heat treat or a sinter to get to full density. And that's what some LPBF processes do require you to do, is go through that heat treat to achieve final density. So luckily, we figured out a way to do this without that. Here's a heat sink we actually show quite a bit. We printed it in copper, and you can see fine features, and again, stable conductivity after heat treat at 102% on this guy. And typically we're again about 100% IICS as built. Yeah, and automotive, here's a good example of an electric motor radial cooling ring. A lot of different applications across many of the industries. Again, these are all based on real customer use cases. I'll give you some time to take a look at these. Yeah, electric motor winding. This is a very popular one. So if you're in the inductance space, this is another great example for you guys. And heat sinks, of course, heat exchanger is always a popular topic. Going to be a good application for copper chromium 2.4, copper chromium zirconium. Something a little bit more stable than just pure copper, which is pretty ductile. This was implicit modeled in 3D Expert. For this specific guy, we're up to 93% IICS. Again, it's geometry dependent. And yeah, this is printed in 4 hours. I'm going to slide through a couple more of these guys again. Heat sinks. There's a CUCR ZR, copper chromium zirconium heat sink. And of course, we have to show a GR Cop 42 and 718 combo. So in this case, we are able to start and print on top of a flat surface. So if we do print this propulsion component we're able to actually re-index on top of it and continue printing, or it could be assembly. And this is a test we did of cladding and printing with a multi-material on top of it. Yeah, so if you would like to know a little bit more information, I'm definitely good on time, right on time. You can come to Formnext, and if you're not mobile enough to get to Germany, that's fine. You'll see our reports from Formnext. You'll see our parts live. We are launching a lot of these copper alloys live. Typically, what we do is we will start to launch stuff even at mid and higher TRL levels, and then if you come engage with us, we'll finish developing for your specific application. So yeah, we'll be talking about at least 5 different copper alloys that we can support at least TRL level 5, 6, and 7, and up to 9. So very ready to start printing for customers. Go ahead and connect with us on LinkedIn. If you have any more specific questions, you connect with me on LinkedIn, and I'm happy to help you out.
Awesome. Thank you, Scott Green, from
No problem.
3D Systems. People might continue adding to the chat. As of now, there's no questions yet, but anyone who's on who has any questions, wants to reach out. Also, Scott, and also I'll say to Jacob from before, make sure to put your contact info maybe in the actual chat so that everyone has access if you guys want, or any
Sure.
materials or stuff like that. We'll continue for now. If anyone has any questions for Scott as we continue, put them in the Q&A, and we'll get back to them as we continue. And we're gonna move forward to our next presentation. Thank you so much, Scott. And
yeah, so good.
Yeah.
There are no questions, so that's awesome.
So good.
Right, guys,
everything was so clear. Everything's
yeah.
Exactly.
Thank you so much.
Yeah, thank you. And we're gonna continue to Thomas Teasley from NASA. Can you hear me, Thomas?
Yes, I can. Am I coming through?
Yep. Let me know if you can share your screen.
It does not look like I can. Are you able to?
Oh, here you go. Now, got it. Okay, I got you. So give me 1 sec. I'll just pull it up.
Sure, quite all right.
Okay.
Perfect. I can see it. Thank you.
Awesome.
Okay. Well, thank you for this opportunity. I very much appreciate it. And I think I definitely agree with Scott. The 3 presentations today are going to be somewhat different from each other, but very complementary, especially since it's geared towards the same topic of copper alloys. Let me give a little bit of background on myself first. So my name is Thomas Teasley. Most folks know me as Tom. I am a liquid propulsion development and test engineer here at Marshall Space Flight Center in Huntsville, Alabama. A lot of my work is actually geared mainly towards the advancement and performance advancements of additively manufactured liquid rocket engine technologies. So how can I get the best bang for my buck? How can I rapidly produce a component? And how can I get the best ISP, the best heat load balance, the best duty cycle out of components like liquid rocket injectors, chambers, and nozzles. So this presentation today is going to be very much geared towards that application and how we're using copper alloys, additive manufacturing processes, and in specific GR cop alloys and what that development has looked like towards liquid rocket engine technologies. Next slide, please. So this is, like I said, on application. You can see several examples here of different liquid rocket engine components, ranging from mixers to combustion chambers, nozzles, impellers, cryogenic fluid devices, and many, many more. These give you a good idea of all the components that we have been developing and advancing towards higher performances, and in particular using alloys like GR Cop. You can see several examples of GR Cop 42 and GR Cop 84 combustion chambers shown here, but more recently we've been working more towards development of GR Cop injectors and GR Cop line nozzles, though there are other materials that may be more practical for nozzles given their low heat flux environments. But for chambers, GR-COP seems to be a clear winner here. And if we go to the next slide, you can actually see several examples of hot fire GR-COP alloy chambers, some of which have been also mated with GR-COP alloy injectors. And these engines, we have tested them very thoroughly in a range of combustion environments, including with different propellants such as liquid oxygen kerosene, or RP1, liquid oxygen hydrogen, and also with methane, several of which have been subjected to the most extreme combustion environments that you can imagine. In many cases with GR-COP alloys, I have been unable to find specific conditions in which you can actually burn through the wall if your coolant channel geometry is designed correctly. And that is another application that we're continually developing, because you no longer have to be limited by traditional manufacturing techniques for coolant channel geometry. You can design a specific geometry to a specific heat flux profile and be able to really reap the benefits of the additive manufacturing process and really push the hardware to its limits in terms of combustion. And if we go to the next slide, this also demonstrates our success in integrating GR-COP alloys in some of the most extreme environments. This last summer, we were very successful in our hot fire test campaign of rotating detonation engines, where essentially the difference between a constant pressure typical liquid rocket engine and a rotating detonation engine is that it is making use of a confined detonation wave. So you quite literally have an instability that is anchoring itself to the back end of the combustor and really subjecting hardware to the most extreme environments that you can possibly obtain. So this just goes to show the resilience and the reliability of GR-COP alloys. Next slide, please. And so right now on our development pathway, a lot of the work that I've been doing has been mainly focused on powder bed fusion based technologies or manufacturing processes using powder in a laser powder bed fusion format, some of which an electron beam powder bed fusion format. But now we're trying to push more towards using directed energy deposition with either powder or wire feedstock in multiple different processes, or even solid state using foil, rod, or powder also in multiple different processes. Next slide, please. And if you are unfamiliar with what powder bed fusion is, this just gives you a quick example of what a typical component looks like on a powder bed, where you simply have a bed of powder, a laser or electron beam will melt a layer of that powder, and then a coater arm will wipe powder back over that and rinse, wash, repeat multiple times until you have a full component. I'm sure everyone is fairly familiar with this process. Next slide. So with combustion chambers and combustion devices in specific, the additive manufacturing process is very, very useful and a very valuable tool in reducing the duration of a schedule and cost, particularly for a combustion chamber. But I don't want to give the impression that there needs to be a switch from traditional manufacturing techniques to additive, particularly for this application, mainly because it is just an additional tool in your toolbox. If there's another type of component or process that makes more sense for a given application, then it's up to the designer to determine what is the most useful for getting the best cost and the best schedule for that component. In the case of a combustion chamber, it does actually make a lot more sense to go the way of additive manufacturing, particularly for making use of such a resilient copper alloy like GR-COP 42 or GR-COP 84. I have had a very difficult time finding it in the wrought form, or at least if I was able to, it's extremely expensive compared to just going with an additive vendor. But just to walk through this process, instead of having to go through finding a liner, casting, and then forming that liner to a specific contour, slotting it via a machining method, and then doing the exact same concurrent development steps for the closeout. That's multiple processes, multiple months of shipping components around the country, if not the world, to get an end product that is several hundreds of thousands of dollars. Whereas switching to additive has enabled us to have a huge increase or rather decrease in your schedule. So in this example, 18 months down to 8 months. And then your overall cost will definitely drop as well, 300K compared to 200K in this example. Next slide, please. This is one of yet the disadvantages to using additive powder bed fusion. You can see a couple of examples of the build boxes constraints in the bottom left. And in rocketry in specific, a lot of engines are very large compared to the typical build box. However, I will say in powder bed fusion in specific, the build boxes have definitely been getting larger over time. And so it may now make more sense to be able to print something like a combustion chamber, but you can easily see how a nozzle, those large bell-shaped configurations on the bottom of the engines, might not make sense to use a powder bed fusion. You're not physically capable of producing the thing as a monolithic component. That's where new processes like laser powder directed energy deposition, or maybe even sticking with a traditional manufacturing process might make more sense. Next slide. And then also, yes, this talk is on the use of copper alloys and specific GR Cop, but again, for your specific application, you need to consult what materials make most sense for you. For combustion chambers, it does make a lot of sense to use a copper alloy for the high conductance and high strength in the case of GR Cop. However, for nozzles, since the heat flux environment is much lower than the chamber, you may be able to get away with a higher strength, lower weight material, such as maybe an aluminum or maybe a super alloy of some kind. So there's no requirement that you use a copper-based alloy for a high conductance environment. You just, as the designer, you would just need to make that trade in your preliminary design analysis. Next slide. This gives a little bit of background, at least at NASA, for example. A lot of this work got started with the LCUSP, or low cost upper stage class propulsion project, where we actually demonstrated a large scale upper stage laser powder bed fusion produced combustion chamber. And you can see an example of that hot fire test on the right. And if you go to the next slide, you can see a lot more examples of which that we've been very successful with integrating channel wall solutions, multiple different closeout configurations to explore lower weight geometries, and really combine as many processes as possible to reduce schedule, reduce cost, and even a couple of examples here of bimetallic solutions that make more sense for a given application. There are also cost reduction strategies by including multiple pieces of hardware or chambers on a single build plate, like the example in the bottom, but that might not make a lot of sense for much larger combustion chambers. Like I mentioned earlier, you may only be able to produce one part per build plate given your build plate size. Next slide, please. Now let's talk a little bit on customization, and next slide one more time. There is a lot of customizability when it comes to additive, and in particular with copper alloys. The roughness factor of the part really is advantageous, especially from a liquid rocket engine standpoint. And if I can backtrack here for a moment, this chamber in specific, we actually hot fire tested it yesterday and demonstrated its success, but it only took us a month to produce it, and manufacture it from design completion to having it on the stand, which is absolutely remarkable. In the last maybe 5 to 10 years ago, if I would have talked to one of my colleagues about producing a chamber in the span of a month, they would have just laughed at that notion. So really the technology has made leaps and bounds in an extremely short period of time. And I for one am very excited to see what is possible in the coming decade, especially with new copper alloys coming to the horizon. Now, with customization, there is the ability to now produce a part and in post-processing, change the part's roughness on critical interfaces. So in coolant channels, for example, you can it may be more desirable to have very low roughness so that you can reduce your pressure losses as much as possible. In the hot wall side, you can now customize it to be rougher or smoother depending on your heat load requirements for the engine. And that also gives the customizability of downstream components. So this is just a chamber here, but because you can tailor that heat load, you can now optimize for the temperature of propellants coming into your injector and modulate your performance, your global performance, like specific impulse or completion of combustion on a downstream level. So now that to summarize here, now that you can customize roughnesses on a chamber side, that impacts downstream things like downstream components like injectors. Next slide. And then the same thing goes exactly for injectors. I know there are several folks out there working on the development of novel injection schemes, and you can see a couple of examples here of shear and swirl coaxial injection. You now no longer have to adhere to specific orifice geometries. You can now produce orifices that are more amenable to powder removal, for example, which is a big challenge, especially with very small holes in an injector face. And then you can also produce components that have quite literally printed into the face a mesh geometry that can transpire fluid of some kind and actively cool that hardware, especially in extreme combustion environments. And then the last thing I'll mention here is also the ability to integrate instrumentation. The injector on the bottom right has several examples of multiple instrumentation ports that would frankly be a nightmare and a headache for a machinist or a designer in a traditionally manufactured component. So now not only are we able to integrate those instrumentation ports, we can obtain a lot more data from a single hot fire test. If you'd asked an engineer maybe 10 years ago, we would be lucky to get maybe one pressure, 1 or 2 temperature measurements in an injector manifold. Now we can take multiple and see exactly how maldistribution is occurring and get a much better picture, much clearer picture of how conditions in manifolds are impacting downstream properties like combustion performance or global engine ISP. And so now we can customize the global engine performance based off of direct measurements in additively manufactured hardware. And one more advantage to copper alloys and GR-COP in specific is its ease of machining. If you talk to any machinist who's ever machined a copper alloy compared to a super alloy, they are much happier. You go through tooling at a much lower rate, and so it decreases component or consumable costs as well. So you don't have to go and purchase or pay for greater machining costs because of the ease of machining. Next slide. And then this just gives another good example of post-processing. So post-processing customization, you don't necessarily have to integrate your best performance capturing techniques or design strategies or technologies within the design phase or even in the print process itself. You can now integrate polishing techniques for the coolant channels or polishing techniques for the closeout of the material to increase fatigue life or increase the ability of the hardware to give you a higher pressure budget in your engine system. So this is just one more customizability of AM hardware that you can see here. Next slide. And to summarize all this work, yes, there has been enormous strides in additive manufacturing, particularly with copper alloys, GR-COP, and specific for our given application. But really the future of the technology is increasing in scale, increasing in design strategies, reducing material costs, increasing or rather decreasing the amount of time it takes to produce a component, and then also combining different methodologies for processing, all with the goal of decreasing costs, decreasing the schedule of a component, and really one of NASA's main goals is making the space access much easier for industry and academia and government, and much lower costs. Because at the end of the day, we very much want a thriving space economy, and additive manufacturing, and in particular copper alloys, have really helped to enable that going forward. Next slide. That's all I have for you. I do have a couple of good references here. Recently, we've been able to publish a book through AAA on an additive manufacturing process. That is a good source if you have not seen that yet. And next slide. I would be happy to answer some questions here if there are any.
Thank you so much, Thomas. We definitely have a couple questions here, and there might be more coming in, as times go by. The first one I see here is for Thomas. Can you comment on the inspection requirements, CT, etc., of AM versus conventional thrusters? I've heard that powder trapping and cooling channels for AM thrusters is a major concern.
Yes, so it definitely is a major concern, and a lot of my work over the last year or two has actually been on how can we integrate new design strategies so that powder removal is not such a large concern. Injectors in particular, if you have a long, skinny orifice, it has a higher propensity to trap powder, and the exact same thing applies for integrated coolant channels. So it has been difficult, but luckily vendors have been getting a lot better about integrating new techniques about how to get that powder out right after the part has exited the build plate. And then we on the NASA side have also been developing new strategies to design channels so that they're not nearly as restrictive, and you can minimize the minimum flow area pass, so you can have a better chance at removing powder. And then on top of that, you mentioned CT scanning. A lot of my work is development hardware. So I can't quite speak to requirements in terms of flight engines, though I would say it is likely that some form of CT scanning confirmation of powder removal is definitely a requirement there. In a lot of my work, we are typically very confident in a lot of the hardware that has been produced for us, especially if it's hardware that is heritage in its design, and we've demonstrated multiple times that can be delivered to us without powder removal. So sometimes we can actually design hardware to where coolant channels, for example, can be exposed, and you can run a simple water flow test to see that each individual orifice is actually free and clear. So that in those situations, you don't necessarily need to CT scan. But in other situations where it might be a high risk component, high heat flux environment, and channels are embedded inside of individual manifolds, yes, it is very much recommended that you do CT scan, though it is not a requirement. I hope that answered that.
Can I jump in and add one piece to that as well? For CT scanning, particularly for powder removal, you need really high energy CT scanning, which can be really expensive to get really detailed and like small pores or looking at that. It can be difficult with standard equipment that's out there. However, we found that you can, if you're just looking for clearing of the powder in the channels, you can use a lower power CT scan, and you can detect if there's powder trapped in those channels. So even within CT scanning, there's some things that you can do to improve throughput and cost and availability of CT scanning equipment for inspection purposes, because typically copper is very difficult to do that with. But yeah.
Yeah, I definitely second that. When we can, we try to avoid the CT scan just because of that cost. But in a lot of situations, you don't have that ability. You must confirm that powder has been removed, because you can't quite afford to put a component on a test or on the test stand and try to run a $10,000 hot fire test only to find out that your hardware was blocked with powder. So that is definitely a concern of ours as well.
Thank you, Thomas and Jacob. So another question for Thomas, and then we'll hop back to a question that was added for Scott. What is the main problem you face regarding the powder feedstock? For example, suppliers, quality, impurities, and so on.
Yes, so with feedstock, because my focus is very much application driven, this is not an imminent concern for me, but it has been made apparent that it is possible, though may not be confirmed yet, that in the production of powder, you may have impurities inside the powder from, for example, the nozzle that sprays the original molten form into the powder atomization process. So there may be some erosion occurring on that nozzle, possibly, and so there might be introduction of impurity or trace metals. Though I believe that those processes have been getting better and better with time, and it likely may not be a concern in future applications or in future components. I myself have tested many chambers produced using different copper alloys, GR-Cop 42 and 84, and I have never seen any sort of hardware failure due to an impurity that I can say for certain. Usually it's more concerns on the print side itself, so build seams, witness lines, high porosity, that sort of thing are more concerns than impurities in the feedstock.
Awesome. So I see, Scott, you already answered one of those questions, so we can jump back to the questions. Jacob, do you want to address the questions that were left for Elementum 3D and other panelists can chime in?
Maybe feedstock as well. One of the things that we found in the feedstock that can really affect the printing and therefore can cause things like crashes on the build or high porosity is the fines. So fines in the GR-Cop we found to be really detrimental, not just because they tend to pick up water faster, which is, I think, the #1 killer of additive powders is water or moisture, but it also then causes the flow of those powders to behave differently. And then that affects the printing process, which then affects the final component. So, and it's really easy to mix in extra fines to then have more volume of powder and less loss because the atomizing is already expensive, particularly in GR-Cop. But certainly I think that is something that we look at very carefully is the volume of fines, because we found that very early on. That was one of the biggest supply chain struggles.
Thank you very much.
Yeah.
Awesome. So before we maybe continue with a few other questions, thank you very much to all the speakers, starting with Jacob Nectarlane from Elementum 3D, Scott Green from 3D Systems, and Thomas Teasley from NASA. It was a great session. Thank you for everyone joining. We're going to leave the chat open and we're going to leave the Q&A open. If any of the speakers still want to address some of the questions that are out there, or post any more contact details or anything that you guys are currently looking for in this market or that you want to get out there, you're more than welcome to join in. But thank you so much to everyone who joined and participated. This was a really educational session, I think, for everyone.
I'm curious to hear the other speakers' opinion of like the copper chrome zirconium. We've had a little bit of experience with it, done a little bit, but generally we've seen a lot of customers shying away from copper chrome zirconium. So maybe throwing that out to the other two to see what their experience with copper chrome zirc has been.
I can't say that I have. Did you say copper chromium zirconium?
Yeah. Yes.
Yeah,
Jacob,
I can't say that I have worked with any specific alloy with zirconium in it. It for us, it has mainly been the copper chromium niobium combinations to date. Though I wouldn't rule it out though for future applications.
Jacob, I can bring up that as I did mention before, that our pure copper does require special optical configuration to get the high-end properties that we supply. But our value by providing copper, chromium, zirconium is that's printable. Every other alloy we have is printable on standard configuration. So if you desire results similar to pure copper, but you're already running or want to buy a machine without a special configuration, you can run copper, chromium, zirconium, and that's like your best closest option. Like, let's say you've already invested in a machine, or you're going to invest in a machine and you want to run aluminum also, or another alloy also, that would be your fallback. Does that make sense? It's an option for people for max machine flexibility. And it's not going to be the same, of course, properties. You're going to make some compromises, but it's in many cases a good substitution, or good enough substitution.
Awesome. Well, thank you all.
Yep.
Great.
Yeah,
thank you guys. Thank you guys for joining. Everyone who attended, the recording is going to be available for everyone. And we'll be posting it online and things like that. So we'll be in touch. And that's pretty much it. Thank you very much. This was a great session.
Yeah, thanks guys. Great to chat with you.
Thank you all.